In the last lecture, at the end of the lecture, we were discussing dimensional analysis. How many people have questions about this dimensional analysis? Did everybody study it and get it? Okay. Those of you who have some questions about dimensional analysis, who are not really sure what this is, please raise your hands. Do you get my question? Everybody, okay, thank you. So now I'll give you another example. Okay. Now, this example is from the notes. Okay. Now we know that when I drop something, it falls. Starting next week, we will learn how to treat this motion, how to get the formulas. At the moment, let's say we don't remember anything about this. We don't know any formulas. Okay? Which is always a healthy approach because we do not want to memorize any formulas. We want to be able to derive how things depend on each other in a simple way. So let's study this simple example. If I take my hand off, okay, this falls down. And if I observe this a bit more, I will notice that it falls down with a faster and faster speed. The speed is changing, so there is an acceleration. Okay? So I drop something from rest. It falls from height, yükseklik, h to the ground in t seconds. Okay. And let me remember that there is acceleration here, and the usual name for this acceleration in falling down is g. So let me call it g. But I don't know its value. I'm not concerned where it comes from yet. I don't know anything about it. Okay? Now, this time, how many seconds it takes for the object to fall to the ground from a height h will depend on some other quantities. What will it depend on? So the question is, I want to think about, figure out, how long does it take an object to fall down to the ground from a height h? This time in seconds will depend on what?
Speed of...
You say mass, okay? It will depend on the height, of course. If I drop it from a bigger height, of course it will take longer, obviously. And it will depend on acceleration. I don't even know it is gravity, but I observe that it's getting accelerated. So how long it will take depends on what is the acceleration. Because it depends on velocity. Velocity is changing all the time. So if there's big acceleration, it will quickly get to high velocity, so it will fall down quicker. But, of course, one of you mentioned a very good question. We'll talk about it a lot. I'm curious, maybe it also depends on this object. This object has a certain mass. So I wonder, I don't know the answer. I wonder if it depends on the mass. Çok yaşa. So here's our question. This time t will depend on g. It will depend on h. And it will depend on the mass. I forgot to mention the mass here. This something has mass, eh? But actually, I've been saying it will depend. I don't know it will depend on it, but it may depend. You know, what is there to depend on? Okay, it may depend on the mass, maybe. It may depend on the acceleration, maybe. And on the height. And how will it depend on these things? Well, let me check that it depends on some powers of these things. And I'm checking this. Okay? So g to the power alpha these, for example, if alpha is 2, it's g squared. I don't know if alpha is 2 or 3 or 1/2 or what. Okay? Now here I start with dimensional analysis. The dimension of t is just time. It doesn't matter, you could say t, but when I talk about dimensions, I usually will use capital letters. Okay, so it doesn't matter. It's t. T will be equal to, now what is the dimension of g? G is an acceleration. Velocity is length over time. Acceleration is length over time, over time again, right? Because how much does the velocity change per second? Is this clear? Okay, so I put here L over t squared to alpha, power alpha, okay. And h, what's the dimension of h? Just L, right? It's just a length. And dimension of m is just m, okay? So this is L to the beta, m to the gamma. Okay? Clear? Okay, so now let's simplify this. This gives us t dimension of t actually. Well, I won't keep writing this dimension. You understand? Okay. So L to the alpha plus beta, t to the minus 2 alpha because I'm dividing by t to the 2 alpha, m to the gamma. Now, this equality sign actually means dimensions are the same here. So I'm not writing the dimensions, but you understand that I'm talking about just dimensions. Okay? So now you can tell me what is the value of alpha? Because this is the trick in dimensional analysis. The dimensions of the basic quantities, how many powers you have, of course, must be the same on both sides of this expression. Okay? So what is alpha? Here I have how many powers of t? Just 1. So minus 2 alpha is the same as 1. Yes, good. Okay. So alpha is minus 1/2. What is the power of L on the left? There are no L's, so it's just 0 power. Okay? Zero equals alpha plus beta. So what is beta? Is 1/2. What is gamma? Okay. So what do I find from this? Let me also find the result. I find that the time for free fall will depend on will be proportional to this sign means proportional to, okay, this thing here. It's proportional to h over g to the 1/2. So the formula that I'm looking for must be something like t equals some constant where this constant is just a number. It has no meters, seconds, etc. It has no dimensions because I took care of all the dimensions. So the formula must be t equals some number times the square root of h over g. Now notice what I found. I found basically how the formula depends. How can it depend on the quantities h and g? And I also found that the acceleration, the time it takes to fall down so many meters, h, does not depend on the mass of the object involved. This is an important conclusion. I think it was you who asked, maybe it depends on mass. It's a very valid question. It's a very important conclusion. It is one of the most important results that Galileo first showed, that the time it takes to fall down is independent of the mass of the object. Now you may ask, well, if it is so simple to show that this formula does not depend on mass, why did it take people so many ages? And Galileo did so many experiments. And you may also ask, well, where is the experiment? You are telling us that in science we learn everything from experiment, and here I do a little trick with some formula and get the right answer, and I discover, it seems, I've just discovered that the result does not depend on mass. How come? Why is it so easy? The reason it's so easy is because in dimensional analysis, I have assumed that the formula, the correct result, depends only on powers. Before doing the experiment, Galileo was trying to see if it depends on mass or not. He showed that it doesn't depend on mass by doing the experiments. And by doing the experiments, he also showed that it depends on h and g according to powers. He found that the correct formula for the distance, the height to fall down in t seconds is proportional to g times t squared. The distance gone in free fall increases as the square of time. This information is found by experiment. The key point is, before doing the experiments, Galileo didn't know the answer, but he even did not know that the answer would be some power of t and g. I have assumed one result in doing dimensional analysis. Dimensional analysis always assumes that the result, the formula, is a power law. But before doing the experiments, we didn't even know that. So the reason this works, and it seems like a magic, in one line you can show, as if without doing any experiments, it doesn't depend on mass. That's because I already assumed that I am going to look for a power law. But before doing the experiments, I don't even know that the result is a power law. It could be some more complicated function. So if you want to show that the time it takes to fall down does not depend on the mass of the objects, you really have to do the experiment with different masses, because you don't know that it's a power law, what the formula is. But once you have some guess, some idea, which essentially comes from some experiments, that the result is a power law, then you can figure out what power of each quantity is involved. Is this clear? Now it turns out, as you will see as we go on in the course, that most formulas that we will use, most of the important laws, are indeed power laws. Okay? Therefore, this dimensional analysis is extremely useful. Why is it useful? When you are doing a complicated calculation, you may make mistakes. Okay? And at the end of the calculation, if you want to check, you have derived some result. Okay? If you want to check if it's right, you just put in the dimensions of everything. And I do it all the time in my research. I make a calculation. I can give you an example. I calculate what is the acceleration for a star, rotating star, spinning very fast, to slow down. And I guess that this depends on the magnetic strength of the star. It may depend on the radius of the star. Okay. It will depend on if there is any mass from another star falling out of the sky. All of these things will have to break it. So I write down a complicated formula, and then I try to calculate something else, and I write down some more complicated formulas. And at the end, I have some formula with, something to the power 13 over 11 times something else, the magnetic field to the power 7 over 15, etc., etc. Very complicated formula. I'm going to use this now. Now, first thing I do is I check it. I just put the dimensions of everything, and see if the right-hand side fits the left-hand side. Or you may just not know the formula completely, some piece is missing, but you have a good guess that it is a power law. Then to see what power it is, just like we did here, you use dimensional analysis. It's also useful for a student, as I said, if at the end of, you are solving a problem for homework or in the exam, and you end up with a very complicated formula. Okay, and you suspect that I have done something wrong. You don't have time to go back to the beginning and check. Just check the dimensions. Okay? So that's what dimensional analysis is about. Any questions about this? Now, let me give one other example of dimensional analysis. In nature, there are some very important numbers. And we have seen some of those already. What do you think may be an important number? Basic, what we call a fundamental constant of nature. The constants whose numerical values we give in the book at the beginning. What are going to be important constants? Gravitational constant, yes. Of course, that's an important constant. By gravitational constant, the really important one is not this little g, how an object that I drop will accelerate. That's important also, but that's only about the Earth, how things fall to the Earth. But the more important gravity constant is a constant that tells you how any two masses, a star and a planet, or two stars, attract each other. We will learn about this later on. But I'm just using it as an example. Okay, I will give you the result. Give you a formula. One example is G. The force of gravity between any two objects, for example, the Sun and Venus, depends on 1 over the distance squared. The Sun attracts Venus, and Venus attracts the Sun back, and they rotate around each other. They orbit around each other. Okay? And this G here is a fundamental constant. Fundamental means it applies to all objects anywhere in the universe. For example, if I write the force between the Earth and the Moon, the formula will have mass of the Earth, mass of the Moon. But the constant G in front is the same G as I write here between the Sun and Venus. Okay? So it's a fundamental constant. It's true for any situation. It is the constant that describes in our units, the MKS units, how strong gravity is. So that's important. That's fundamental. Okay? Another important constant is this. We will learn in the course that there is a property of particles called charge. This is responsible for all electric phenomena, and a proton and an electron attract each other with this electrostatic attraction. If you don't know what it is, don't worry. I'm not trying to teach you about it. We will do that later. I'm just using it as an example. Okay? Proton, electron attract each other, and the attractive force depends on 1 over the distance square. It depends on their charges. Their charges are plus E and minus E. They have the same magnitude of the charge, same number, times a constant K in front. So the force of attraction in an atom, in a hydrogen atom, proton, electron, has this combination of constants. Not just K, but I put the E square in there, because in any atom, maybe it has 5 protons, then I put the number 5 in front. But charge of each proton and the charge of an electron is the same in any kind of atom. Hydrogen, helium, boron, whatever you want. Okay? So K times E square is going to be fundamental, because all atoms all over the universe are the same kinds of atoms. Alright? So K over E square is going to be a fundamental constant. What does it describe? It describes how strong the electrostatic force is. Okay? Now I'll mention another fundamental constant, which most of you have not heard of, and we will learn about this one also later in the course. This is pronounced H bar because of this sign on top. This is a fundamental constant. We'll learn about it later, but it is the constant of quantum mechanics. And what it describes is, in quantum mechanics, inside atoms, we find from experiments that electrons and protons are not just particles the way we think of a piece of stone or a bullet. They are sometimes like particles, sometimes they are waves. And this constant is the fundamental constant that describes when and to what extent some object is behaving like a wave, and to what extent it's going to behave like a particle. The very strange, funny relation between particle properties and wave properties is described by this constant. Okay? Just know this much. We don't really understand it yet. We haven't discussed it. But I'll just use it here to give examples. This is the Planck constant. And there's another fundamental constant that I'll mention, which we already saw in the first lecture when we discussed Einstein's formula for adding velocities. What was that constant? The speed of light. Why is that a fundamental constant? Because, as we discussed, it is not just light. It is the speed of all kinds of electric magnetic waves, like radio waves, X-rays, ultraviolet, whatever. Okay. Moreover, as we will find later in the course, this speed c comes up in fundamental equations called Maxwell's equations in a way that does not depend whether the experiment is done in a train or on the station platform or where. Okay? It is a velocity that appears in the basic laws of nature that does not depend on who is observing it, at what velocity. So it has this funny property, the speed of light, that two different observers measuring the speed of light, and these two guys are moving with respect to each other. Okay, I'm at rest and somebody is running past at 50 kilometers. No, it's bad. Somebody is running, so it's maybe 5 meters per second or something. Whatever, okay? We both measure the same c. So it is a fundamental constant. It's a constant velocity that appears the same to everybody, no matter what that person's motion is. Okay? So it's a fundamental constant. Now, next thing I'll do in this example is to figure out the dimensions of the fundamental constants. G, m1, m2 over r squared equals a force. This is how we define the gravity, how the observations show us where the gravitational constant appears. Okay? So to figure out this dimension from this result, that it gives you how strong the force of attraction is between the Earth and the Moon or whatever. Okay? Then we must know something about force. We are just beginning the course. We don't know what force is yet. So I just give that to you. Okay? Force is the property that affects how motion is changed, and as Newton discovered, if there is some attraction, repulsion, some other objects are affecting this object's motion, then this effect, the force, will give you the mass times the acceleration. Okay? This is acceleration. And what this thing is this formula is Newton's second law. Again, don't try to understand it because I'm not teaching it yet. I'm just going to use it as an example. If you have never heard of it, don't worry. Okay? So F equals ma. What I've used it for is to figure out what the dimension of force is. F equals ma is the general law of motion that applies for all kinds of forces. So it tells me what kind of quantity is this force, what's its dimension. Okay? So dimension of force is m mass. Now what is the dimension of acceleration? We just figured it out. L over, okay, and our fundamental dimensions are m, l, t, so this is dimension of force. It has 1 m, 1 l divided by 2 t's, 2 powers of t. Okay? Now I can proceed to find out what's the dimension of g? units of G. I will not do it now. This is homework for you. It's also in the book. You can read from the draft notes, or you can just figure it yourself, because I give you the formula. G N1 N2 over R square is F. You know dimensions of F. N1 N2 R square. Figure out what dimensions of G is, and what are the units in terms of meters, kilograms, and seconds. You do that later, but please do it just to give you some practice with dimensional analysis and units. So this is homework for you. I'll do the next one. Let's find the dimensions of this KE square. Okay? KE square over R square is F. If I now write dimensions of KE square divided by, what is the dimension of this R? Well, what was R? I just introduced R. R is the dimensionless? R, okay. R is the distance between the electron and the proton. So what's this dimension? It's a length. So I have here an L square, and what was the dimension of F? Well, we just did it. Let's go back to the last page. Here's the dimension of a force, okay? So let's do that. So this KE square will have rather complicated dimensions, units. It will have L times how many powers of L? 3 divided by T square. Okay? So just the constant, a fundamental constant, Ke square, which occurs all the time in atomic physics, in chemistry, okay, has rather complicated dimensions. And its units will be, Ke square is in units of kilograms, meters cube, divided by centimeters square. Sorry, seconds square. Okay? Now, here is the next question. I have these fundamental constants, like this one, which concerns atoms. Another constant that concerns atoms is h bar, because we know from experiments that sometimes they are like waves, and this is what tells us, this Planck constant. And atoms, we know, emit light or absorb light. So another fundamental constant about atoms is the speed of light, c. Okay? My question now is, let me compare the dimensions and units of these fundamental constants, Ke square, h bar, and c. How do they compare? How do they relate to each other? A more fundamental question is this. Is it possible to make a combination of fundamental constants which is dimensionless, which doesn't have any dimensions? Why is that important? Well, it's important because if I can find a dimensionless number, a number that doesn't have meters, second cubes, and things like that, okay, then that number is really fundamental because it will not even depend on what system of units you use. So it is not telling something about our technology of measurement. It's telling us something about nature. If you can find a combination of experimentally measured fundamental numbers, which turns out to be itself without units, without dimensions, then that combination must be really fundamental. It must tell us something important about nature itself. Right? We'll see what it tells us. Okay? So here is the question of this exercise. Here's the question. I'll leave gravity aside for the moment. I'll just concentrate on electric stuff because I know what, well, we haven't seen yet, but we will learn that light is also an electromagnetic phenomenon. Atoms emit light, etc. So I'm trying to learn something about this fundamental force in atoms, whose constant is Ke square. But this is complicated units. Now I'm asking the question, if I put in H bar and C and compare with K times E squared, the electric force, is there some number I can fish out which will have no units? And that's going to be important because that number will tell me something about nature. It will not depend on my way of measurement. Clear? Okay, now I'll just take a shortcut and give you that number and show you its dimensionless. To do this, of course, you must know what the dimensions of H bar and C are. Okay? Well, you don't know. I assume you don't know anything about H bar, so I give you its units. Okay? Or units are kilogram, meter square per second. So dimensions are mass, this is meters of course, mass L square T to the minus 1. Okay? What is the dimension of C? Speed of light. What is the dimension of C? Speed of light. Meters per second. What is the dimension? L over T. Right. Good. Okay. So this is L over T. And Ke square, we figured out, was what? It's the dimensions of M, L cubed, T to the minus 2. Right? Now, let's save time. I mean, I could ask you this and we could play around and find the answer. But I'll just give the result to you. Dimensions of this combination of fundamental constants is M to the 0, L to the 0, T to 0. That means it doesn't depend on any mass, length, or time. Dimensionless. It's a pure number. And its value is 1 over 137. This is a very important number. So it's given a name. This is a definition, of course. When you give something a name, that is not an experimental or mathematical result. Okay? A name has no proof. You just like that name and give it. So this is a definition, 3 lines. The name I give it is alpha. Fine structure constant. This is another use of dimensional analysis. By knowing the dimensions of several important quantities, I can ask if there are powers of those quantities that give you a dimensionless number. If there is, this is going to be important. Why? Because if you can find a dimensionless number, just a pure number, without any kilograms or centimeters or meters or whatever, okay, that has to be important in nature, because it doesn't depend on our units. Okay? Now, what does this number tell us? It tells us that the strength of electricity, the strength of electromagnetic interactions, in some fundamental sense that doesn't depend on our units, is 1 over 137. For this to make sense, we should compare it with other interactions, other forces in nature, to figure out which is more important. Right? For example, we can compare it with the gravitational force. Now, the gravitational force is G times M1 times M2. M1 and M2 could be the Earth, the Moon, a planet, an atom, whatever. Yourself, okay? So that's not really fundamental. But to discuss the gravitational force in a fundamental way, I should put there masses of basic fundamental particles. Now, I want to compare it with electricity. To do electricity, I use E squared there, Ke squared. Why? Because in atoms I have electron and proton. So, to compare gravity there, what masses should I put? The masses of? Does everybody understand the question? Okay, let me repeat the question. I learned something interesting about electricity. I found that the electric force, if I play around with these dimensions and so on, has a pure number, which is 1 over 137. Now I ask, here's the question. Let me compare it with the gravity force. Can I find such a dimensionless number for gravity? I ask you this, and you can come back and tell me, well, gravity between what? Because gravity depends on masses. So I say, well, what things did I use in electricity? I used the electron and the proton. So to compare the gravity of the same things, I should put there the masses of electron and proton, right? I mean, it doesn't make sense to compare one formula for electron and proton for electricity and for gravity, the Earth and the Sun. You know, it's apples and pears. Okay? So I go back and put there in gravity G, M electron, M proton. What is the dimension of G times M electron times M proton? Well, let me go back. Here, G times M1 times M2 divided by R square is a force, just like K times E square divided by R square is a force. So G times M electron, M proton, that combination has the same dimensions as K times E square. So that's okay. But the numerical value will be different. Okay?
Could be possible.
What?
They have to be same or different forces?
The dimensions, no. The forces are different. Masses are different. The numbers will be completely different. That will be your homework. But the dimensions of G times M1 times M2 must be the same. Its units must be the same as K times E square. Because K square over R square is force, G M1 M2 over R square is also force. So G M1 M2, its units must be the same. Its dimensions must be the same as K square. Clear? To compare with proton electron, of course, M1 and M2 should be mass of the proton, mass of the electron. So now I go back. Dimensions of that must be the same as Ke square. Dimensions and units are same, not the numbers. Okay? So G, M electron, M proton over H bar C will give you a dimensionless number. Homework, find its value. And then you will find that G, M electron, M proton over H bar C is much, much, much less than Ke square over H bar C, which is 1 over 137. So this will tell you that gravity between the electron and the proton inside the atom, independently of anybody's units, as a pure number, gives you a fundamental constant, dimensionless constant, G, M1, M2 over H bar times C. Whatever that is, you can just go home and look up those numbers from your book and calculate. Okay. You will find out that it's, of course, it's going to be dimensionless. We already know it's dimensionless. Okay? But its value will be tiny compared to E square over H bar C. Okay? This just says that within atoms, gravity is negligible. Now, if you go inside nuclei, there is this strong force. inside nuclei, strong force. Okay? So the strong force constant, we will never learn about this, but I'll just give you a result. There's a constant that tells you how strong is this strong force between protons inside an atomic nucleus. Okay? It's a number and it has units. If you take that number and divide by h bar over c, that's also dimensionless, and it's a number that's of the order of 1 to 10. So it's much larger than your fine structure constant. So what this example tells you is, although I haven't done it all in detail, if you can find combinations of fundamental constants of nature that, when you multiply and divide, do not have any units, these must be really fundamental because they don't depend on our units. And then you can compare such constants for different types of forces, like for gravity, for electromagnetism, and for the strong force. And that tells you that in a fundamental sense, it doesn't depend on our units at all. Gravity is much, much weaker than electromagnetism, but electromagnetism itself is much weaker than the strong force that powers the nuclear reactors and the stars and so on. Okay? Any questions? There are more examples and problems, etc. in your book. All the values of the constants are given, so you can do this one as homework. Okay, I already said it's homework. And I'm sorry this is now late. 10-minute break. In the next lecture, we start on